So welcome to Physics Live with Angan Bhattacharya once again. Today we are going to discuss the eightfold way representation in the particle world. So as it is clear from the title that it is regarded as a periodic table of particle physics. So myself Angan Bhattacharya from the Department of Physics, Visheshwariya National Institute of Technology, Nagpur, studying the MSc in Physics second year. So let's start to discuss the introduction behind it. What is the importance of this eightfold way scheme? What led to discover this eightfold way representation? Let us discuss this thing. So at first we will start from the classification of the subatomic particle. Subatomic particles are broadly classified into two classes, leptons and hadrons, out of which leptons corresponds to the elementary particle, smallest indivisible elementary particle, that it cannot be breaked into further smallest particle. And the other feature, more important feature, is that they do not experience any strong interaction. Now it is very well known to you what is strong interaction, what is weak interaction, and what are there are four types of interaction: gravitational interaction, electrostatic interaction, or Coulomb interaction we can say, strong interaction and weak interaction. So out of which the leptons do not experience strong interaction, whereas hadrons experience strong interaction. So let us start from the leptons. So leptons are basically elementary particles that cannot be made of any other particle. Some of the example of leptons are electron, muon and tauon, as well as electron neutrino, muon neutrino and tauon neutrino. Whereas hadrons are classified into two classes: mesons, which includes pi plus, pi 0, pi minus, k plus, k 0, and the anti-kaons k 0 bar, k minus and singlet eta, and the baryons, which include sigma plus, sigma 0, sigma minus, sigma, xi 0, xi minus and lambda 0, neutron, proton, etc. Now mesons corresponds to the bosons, that is they have the spin of integer multiple of H line, and the baryons are corresponds to the fermions, which have half odd integral spin. So from the very basic classification of lepton and hadrons, we had discussed that leptons cannot be divided into further elementary particle. But what about hadrons? Are the hadron particles are elementary or fundamental? To discuss these things only, eightfold way representation scheme was started. So the eightfold way representation was given by Murray Gell-Mann, and in the year of 1961 he wrote the paper, which was received in 1964 by Physics Letter, and it is based upon the schematic model of baryons and mesons, which is basically known as the eightfold way representation. So what is this eightfold way representation? This is one of the straightforward idea to express the hadron particles as multiplates, like neutron and proton, which have more or less equal masses, as can be evident from this 939.6 MeV per c square, and proton has the mass of 938.3 MeV per c square. So since the strong interaction does not depend on the charges, so neutron, proton, 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 or proton, neutron experiences the same strong interaction. So we cannot classify them. Therefore they form as a doublet. Again, the multiplicity arises from another quantity known as isospin. Suppose in every groups, okay, to distinguish one group from the another, we have the quantity isospin, which has far relation from the spin. It is not the spin, although it is name is isospin, but it is very different from the spin concept. Okay, so this forms a doublet, that is a group of isospin whose multiplicity is 2. Next thing is sigma plus, sigma 0, sigma minus. Like the similar way only, it has a more or less equal masses, that is 1189, 1193 and 1197 MeV per c square respectively. So they form as a triplet. That is the multiplicity as per the isospin is conserved. Its isospin is 1, So its multiplicity is 2i plus 1, which is 3. Okay, so they form as triplet. Similarly, xi0 and xi minus also form doublet. Okay, so we can arrange these multiplets as in a row, in a single rows. The multiplets we have arranged in a single row. Okay, so this eightfold way representation was independently given by two scientists, Murray Gell-Mann and Yuval Newman, and they thought that these particles can be represented like this thing. That is, they have connected those particles like some geometrical shapes. Okay, so you may think that why this particular scheme is taken, why this particular geometrical shape is taken. Is there any way to represent or way to choose which shape will fit to this representation? I will soon discuss with you this thing. So it is known as the eightfold way scheme. What is this? It is an organization scheme or classification of the hadron particles in groups or charts or geometrical patterns based upon the same spin. That is, each of these hadron particles have the same spin, but they have some different charges as well as different strangeness. Now I will discuss what is this thing. So let first discuss what is the motivation behind this eightfold way scheme. So some scientist believes that the motivation behind this eightfold way scheme that was given by Gell-Mann was from the noble eightfold pathway from Buddhism, which stands for right speech, right action, right livelihood. These three forms a pillar of the moral virtue, and right effort, right mindfulness, right concentration forms the meditation, and right view, right resolve forms the insight or wisdom. These are the eightfold pathways as per the Buddhism is in noble pathways of Buddhism. It is given like that. So it is a way of living the more philosophical life. Okay. Another scientific motivation was their periodic table, which was given by the Mendeleev, and it was a tremendous important in the scientific aspect. Like the chemistry and physics people very much bothered about this periodic table, because periodic table is something which accumulates all the elements and arrange them in such a manner that we can easily study each of the elements property very easily. Okay, so like that only Murray Gell-Mann was very much eager to represent these elementary particles, represent these hadron particles based upon some properties such that it will be easier for us to study them and to search for whether these hadron particles are elementary or not. Sometimes, thus, Murray Gell-Mann hailed as the Mendeleev of subatomic world. Now, what is the representation scheme? As I have already asked to you, are these arrangements random? Like that we have connected these elementary particles and formed some hexagonal shape. So, are these arrangements are random? Answer is no. Why? Because I have already discussed that eightfold way is the organization scheme based upon same spin, a geometrical representation based upon same spin, but different charge and the strangeness. Now, what about the strangeness? We all know about what is charge. What about the strangeness? When scientists were studying the high energy physics, they found certain particles that are created by the strong interactions but decay through weak interaction. This was very much strange to them, so they named as those particles as strange particle. Now, to distinguish this strange particle from the other particle, the scientists were given this particle some quantum number, which is strangeness quantum number, like the other cut of the strange particle. This is the other cut of the strange particle. Now, next question is how to get this strangeness quantum number. This was also resolved by Gell-Mann by his famous Gell-Mann-Nishijima formula, which stands as 2q bar equal to s plus b. What is q bar? Is the average charge of the given multiplet. Like if the neutron is concerned, then neutron and proton forms the doublet. So the average charge 1 plus 0 by 2, that is half. So 2q bar is 1. So the 2q bar quantity for the neutron as far the doublet is concerned is 1. And neutron is a baryon. Neutron is not a baryon because neutron is baryon basically because it is spin half. I have said already that hadrons are classified into two classes, mesons and baryons. Meson stands for the bosons which have integral number of spin, but baryons are the half odd integral spin. So neutron is baryon basically, and for neutron 2 q bar is 1. So the baryon quantum number for neutron is also 1. So S should be 0, so that the neutron is not a strange particle. And it is evident that neutron is not at all a strange particle because it does not satisfy the requirement for being a strange particle. Okay. So from that equation only we can get S equal to 2 q bar minus B. Now the eightfold way stands for the representation based upon same spin but different strangeness and charge. So these row elements are taken in such a manner that they have same strangeness, and the diagonal elements are diagonal particles are taken or arranged in such a manner that they have the same charges. This is the scheme of representation in eightfold way. Now why I called them as eightfold way representation, it has some more mathematical aspect, but I will not go into the details about this mathematical aspect. For that you have to study the group theory, which is a far more big topic for us to discuss. So I will just give the message that it stands from the special unitary group. As you know that SU, and if I consider n cross n matrices corresponding to n cross n complex elements such that its determinant is 1, then only it is known as special unitary. Unless u dagger u is satisfied by 1, then it is simply called unitary. But one more constraint is there, that is the determinant of the matrices should be 1. So this constraint determines or restricts the number of free parameter or generator to the group as n square minus 1. So if we consider the SU3 triplets, SU3 groups, then the number of free parameters or generators will be 3 square minus 1, that is 8. From that only the eightfold way name was given. So let us discuss the spin-off hadrons as it is shown in the slide. That spin-off hadrons consist of neutron, proton, sigma and xi particles, and it is arranged based upon the same strangeness, same charges, etc., and it is given like that. Okay, so there is a spin 0 hadrons which is a meson octet. Now eta dash particle is also discovered. So we have now meson nonet, but it is not represented here. Meson octet is taken, but now it has been modified meson nonet. Okay, so these includes the counts, pions and anti-counts. Okay. And again the same scheme is followed, same strangeness are taken in a row and same charges are taken in a diagonal. So similarly, if we arrange the spin 3/2 hadrons based upon this, the multiplates, same strangeness in a row and the same charges in the diagonal, then we can form this triangular like shape structure, geometrical pattern. Okay, now the interesting thing in this spin 3/2 hadron representation is that although I have named here that it is known as baryon decoupled, but it consists only 9 particles. Where is the 10th one? It should be in a position such that this particle should have strangeness minus 3 and charge minus e, but at that time there was no any particles which can satisfy these two conditions. But Gell-Mann was very much sure about the existence of last particle to satisfy the decouplet condition. Okay. So the missing particle was found in the year of 1964, which is known as the omega minus particle. And here lies the superiority of this eightfold way representation. So you come to know that how important is eightfold way scheme. Okay, that it can predict some particle may exist which can have the different strangeness, like strangeness minus t and charge q minus e, such that we can express these in the eightfold way. So his prediction was right. Now the complete decoupled structure is given like that. Next importance, I have already discussed that this can predict the non-discovered particles which should be present to satisfy this eightfold way, and it was discovered after the discovered by the experimental high energy physicists that there should be such type of particles. Now the importance is that it is regarded, as I have already told you, that it is regarded as a periodic table in the particle world. Now what is the significance of the periodic table? We have the arrangement of elements there which are different, which have some different properties, like some of the elements are gaseous, some of the elements are liquid, some of the elements are solids, some of the elements are radioactive, some of the elements are highly electronegative, some of the elements are electropositive, some of the elements are transition elements, some of the elements are what can I say, have some different small atomic size, some of the elements are big atomic size, all these things are there. Now why there is some diversity? What is the cause behind it? It is the inbuilt structure of the elements, which is composed of electron, proton and neutron, and their arrangement, number, etc. is develops this certain diverse properties in these elements. So this gives some idea that the different properties of these hadrons may be possible if we assume these hadrons to be composed of more fundamental, more elementary particle, such that their proportion depends, their proportion will reflect on the overall properties of these hadrons. Based upon this only, Gell-Mann gave the Quark model. Gell-Mann proposed that the hadrons are composite particles formed from more fundamental constituents, which is known as quarks, whose internal configuration gives rise to these diverse properties. Now there are three basic types of quarks, U, D, S, which can also be represented in the eightfold way representation, like the same strangeness are in a row, same charges are in diagonal. So U, D, S, there are three basic quarks, and their antiquarks also exist, U bar, T bar and S bar, which has the opposite kind of nature of the quarks, like those have the charges minus 2 by 3 for U, and for S and D it is plus 1 by 3, and strangeness is bar, the strangeness of S bar is plus 1, strangeness of U bar D bar is 0. But here lies some problem. You can see here that U, D, S have the fractional charges, and which should be there because the overall charges of the hadrons are integer. Okay, so we must assume that there should be fractional charges present which are elemental to constitute the hadrons. But the problem is that even today also we are not able to measure these fractional charges. Then how can we believe this thing? Gell-Mann said thus, that he suggested that the quarks are bound together by some strong interactions, so that we can never found to be never found them to be free. Okay, so here the Quark model, as per the Quark model is concerned, all baryons are assumed to be made up of 3 quarks, and all antibaryons are made up of 3 antiquarks, and the mesons are made up of 1 quark and 1 antiquark, Q bar. So if we take one or two examples, then it will be clear to us what is the superiority of this Quark model. So the neutron is assumed to have UDD quarks. So if we find the total charge, it is better to say that UDS have the half spin equal to half, because of the similarity of them to the leptons. Only difference is that it has fractional charges, whereas the leptons do not. Okay. So the total charge corresponding to the UDD is plus 2 by 3 minus 1 by 3 minus 1 by 3 gives rise to total charge 0, and the total strangeness is also 0 because no S quark is there, which satisfies the condition of the neutron to be present in the eightfold way scheme, to be the set position. This strangeness is 0, charge is 0. Okay. And if we take another example of pi plus, because it is a meson, then there should be one quark and one anti-quark. So U and D is there such that the total charge becomes E and the strangeness becomes 0, which also satisfies the condition that pi plus has the strangeness 0 and charge is plus E. Okay. So at this moment I would like to stop the discussion of this eightfold way scheme. The more rigorous mathematical proof I have omitted because of the lack in time. So if you wish, then we can continue in some another video. Okay. So these are the references that I used for this preparation. You can also refer these things. Introduction to Elementary Particles by D.J. Griffith, Gell-Mann's paper, The Schematic Model of Baryon and Meson, and I have taken this periodic table picture and noble eightfold pathway from these sites. Okay, so thank you, thanks for watching.